College, London, UK.
Hello.
Hi, doctor. Please start your presentation.
Okay, I'll start first sharing my screen.
Yes, doctor.
Do you see my screen?
Yes, doctor, we can see your screen.
Okay, you see it well?
Yes, yes, doctor.
Okay, thank you. So I'll start then. So thank you for the opportunity to present our work here. I'm Salvador Eslava from the Department of Chemical Engineering at Imperial College London. And the title of my presentation is Engineering, Photoelectrochemical, and Photocatalytic Materials for Solar Fields. So we know that the world energy requirements continue to increase. This is due to the increase in the world population. And this is also increasing the amount of fossil fuels that are used, because although we are decreasing their percentage, we're still increasing the energy demand. So we need to change this trend to be able to tackle the global climate change. And if we see at abundant renewable energy sources around, we see that the sun supplies the current world energy year consumption in less than 1 hour. So it looks kind of obvious that the sun is going to play a key important role in the future of the wide diversity of energy sources. An elegant and potentially efficient way to use the solar energy is using semiconductors that absorb the solar light and then they generate charges that can induce different redox reactions, such as the formation of carbon monoxide from carbon dioxide, or methanol or methane from carbon dioxide, or hydrogen from water. And then these fuels and feedstocks can be used to power our vehicles and devices, or as feedstocks in the chemical industry. There are different ways to use these semiconductors in devices to harvest the solar energy. We could have the semiconductors in photovoltaics and then connect the photovoltaics to electrolyzers. So this way we can, for example, form hydrogen and oxygen. This is photovoltaic plus electrolysis configuration. We can also have the semiconductors in photoelectrodes as part of an electrochemical cell where we separate the oxidation and the reduction. And we have the electrolyte touching the semiconductor. Or we could have no electrodes, just powders or suspensions, where we directly convert the carbon dioxide or water to fuels using the solar energy. This is the photocatalytic field. And there are also configurations in which we combine these three different types. In my group, we are mainly working on photocatalysis and photoelectrochemistry. So we still do some of photovoltaics because actually some of our photoelectrodes are prepared first as a solar cell, and then if they work, we use them as photoelectrodes. And actually all these three configurations are very linked, so any advance in one benefits the others. The targets for photocatalysis and photoelectrochemistry is to achieve more than 10% solar to fuel efficiency. This would enable their commercialization and their scaling up and many others. The challenge is that at the moment the efficiencies are low due to electron and hole recombination and poor catalytic surfaces and/or sluggish kinetics. We know that this is a long path to achieve an efficiency higher than 10% with photocatalysis or photoelectrochemistry, but it's also at the same time a path full of opportunities to develop materials that are useful for a wide range of technologies such as photovoltaics, electrolysis, sensors, and electronic devices. The solar spectrum is quite wide. We have UV light, visible, and infrared light. So the devices to absorb the solar light should have different bandgaps. So we should combine more than one semiconductor to be able to absorb the different solar spectrum. And here we can see different semiconductors that can be used in these photocatalytic or photoelectrochemical devices, also in solar cells. We have, for example, copper oxide, zinc oxide, tungsten oxide, titania, etc. Many different ones. Some are good for oxidations, others are better for reductions, or some absorb more in the UV, more in the visible. So they are all different, but all useful for different parts of our devices. In my group, we have been working on many different semiconductors, such as hematite, bismuth vanadate, titania, and perovskites. And here I will show you some examples of the work we've done. We can see that these semiconductors, they have a conduction and valence band that straddles in different ways the different redox reactions that we can consider. So we'll start with titania. So when I started on titania, I was at the same time working with graphene oxide. We've seen just before a previous presentation on graphene oxide. This is a material with high aspect ratio, incredible properties. And the high aspect ratio, so its two-dimensional shape, could also be interesting for photocatalysis. So I was trying to mimic this two-dimensional shape, and eventually found that we can mix graphene oxide with these clusters where we have a core of titanium and oxygen stabilized with 32 ethoxides. We mix this in THF, stirred in 10 minutes with graphene oxide, evaporated and heated up to 450 degrees. And this led to the formation of titania flakes that mimic the two-dimensional shape of the graphene oxide. This high aspect ratio was very beneficial for the eventual photocatalytic evolution reaction. We could see the hydrogen evolution when using titania. For titania prepared just with clusters, the hydrogen evolution is small. If we use one of the best benchmark titania materials, we obtain some micromoles per hour of hydrogen. However, with these nanoflakes, thanks to the high aspect ratio and the preparation method, we achieved more than 4 times an increase in the hydrogen evolution. We also used other clusters, in this case, titanium 7 with 4 oxygens and 20 ethoxides, and aerosol-assisted chemical vapor deposition. And we deposited films that initially were very black because we are using nitrogen, but after calcination in air, we obtained titania films that, as we can see in the microscopy images, they have very nanostructure, very interesting nanostructure. They are like flowers, like desert roses, that probably you have there some in Dubai, which show a lot of different facets, We did a lot of XRD diffraction and TM analysis, and based on the angles and the lattice fringes, we concluded that the petals of these nanostructures, of these roses, expose preferentially the 010 facet, which is one of the most photocatalytically active facets of titania. And this was unique to the use of these type of clusters. When used different precursors, such as titanium ethoxide, we were just forming an amorphous or crystalline titania, but without the 010 facet exposed. We tested the photocurrents in these photoanodes, and we could achieve very good photocurrents for all the different light sources, for simulated sunlight with chopped light or with UV LED, very good stabilities. And when we measured the incident frontal to current efficiency, we could see that this was 100% at 350 nanometers. So this shows that we achieve 100% when we managed to irradiate the band gap. And these good photocurrents were related to oxygen evolution. So we didn't have any other reactions, since we measured more than 90% Faraday efficiency. We also tried to extend the absorption to the visible range. And for that, we used these clusters, where we have molybdenum and titanium oxocores. And these, following a spray pyrolysis, we achieved these films that upon calcination had, you cannot see it very well in the pictures, but they are a bit more glimmer. And so when we measure the IPCE, we can see that compared to titania, we are shifting the efficiencies to higher wavelengths. So this shows that we have narrowed down the band gap. The problem is that these clusters, they don't expose the 010 facet. So we didn't achieve efficiencies close to 100%. But still, we observed an interesting shift of the bandgap to larger wavelengths. We have also studied other semiconductors, such as iron titanate. Iron titanate has interesting properties between those of titanium and iron oxide. For example, it absorbs the solar light. We have a bandgap, it has a bandgap similar to that of iron oxide hematite, bandgap around 2 electron volts. Still prepare iron titanate with abundant metal sources, such as iron and titanium. It's non-toxic, because iron and titanium are not toxic. The challenges with iron titanate is that they are more difficult to see. It's more difficult to synthesize. Often you have segregation of phases. There's also a lack of knowledge of its properties because it's relatively novel material. We endeavor ourselves to study this material, and we used AHCVD, aerosol-assisted chemical vapor deposition. And we found that using titanium isopropoxide and iron acetyl acetonate was in ethyl acetate and methanol was a good combination to prepare iron titanate-based films. But as you can see here, we have a lot of different phases. We tried to minimize the formation of secondary phases, and eventually we found that if we add a little bit of zinc acetate, we will have a boost of the formation of iron titanate phase, and just a bit of hematite as a secondary phase. But we avoid the formation of titanium rutile and this other secondary phase of iron and titanium. We've analyzed the X-ray diffraction results, and we could see an increase of the unit cell, which is assigned to the interstitial position of zinc 2+ in the unit cell. We also saw some shifts in the XPS peaks, for example, in the titanium 2P peaks. We see a shift that we assigned to the presence of more titanium 3+ centers, more oxygen vacancies, and also we saw in the iron that we have some more iron 2+ centers. We measured the photocurrents and we tripled the photocurrents. So the addition of zinc that boosts the iron titanate and avoids the formation of secondary phases that we don't want has a beneficial effect in the final photocurrent. We measured the incident photon to current efficiency, and this was more than doubled in agreement with the best photocurrents. We measured doing analysis of mode Schottky. We know it's a bit tricky because this is a very porous material, but it's still, it gave us some qualitative measurements. And this showed that the charge carrier concentration increases 4 times when we have the zinc 2+. And this agrees with having zinc 2+ at interstitial positions. Also in agreement, when we constructed the energy diagrams from some measurements in the same XPS tool, we could see that we have a shallower Fermi level, which is related also to the increased charge carrying concentration. So the best photocurrents are achieved because the zinc promotes the iron titanate phase, promotes the formation of better absorption, better charge carrier, shallower Fermi level that will increase the band bending, etc. All beneficial effects to have better photocurrents and oxygen evolution. We also studied a lot iron oxide. So it has very good properties because it's prepared for the abundant material. It has a bandgap of 2.3 electron volts. So yeah, so it's very interesting material. It's just rust, but it shows very good activity as a photoanode. When we started to work on this material, we could see that a lot of films in the literature were prepared with particles that were prepared by the use of iron pentacarbonyl. And iron pentacarbonyl is a toxic precursor. And we studied then alternative ways to prepare those particles to be used in the preparation of hematite. We found that we can use deep detected solvents and that use iron nitrate instead of iron pentacarbonyl. So we found this way a greener way to prepare the iron particles, because also the deep detected solvent is greener itself, is prepared with choline chloride, which is a food additive, and urea, which is a fertilizer. So it's cheap and non-toxic. And we and it allows us to use iron nitrate. And yeah, and we obtained good photoanodes, similar to the ones prepared with an iron pentacarbonyl toxic source. We also saw that there is a lot of research on Dr. blading of the hematite films, but Dr. blading is not so reproducible as spin coating. So we tried to develop inks for spin coating, and eventually we found that we can use the iron oxide particles, a bit of chlorhydric acid that partially dissolves the particles, and this copolymer that works to disperse the particles in the suspensions, in the inks, and to generate final porosity at the end. And this way we could prepare very nice inks that form nice photoanodes with very good photocurrents. So these were methods to prepare hematite. But then to improve the hematite itself, we also need to add an extra layer on the surface to help in the reaction oxidation, in the oxidation of the water, in the kinetics, which are very difficult because they involve 4 holes. And we studied different methods. We studied, for example, the addition of cobalt iron oxyhydroxide. And also the simultaneous addition of iron oxyhydroxide on the surface. I'll show you first the addition of cobalt iron oxyhydroxide. We did a systematic study, adding different amounts of cobalt iron oxyhydroxide by following different deposition cycles, sweeping the voltage between 1.35 and 1.65, and repeating this. So eventually we have different layers of cobalt iron oxyhydroxide on the surface. If we just do 3 cycles, we have less than 0.7 nanometers of the electrocatalyst on the surface. If we do 30 cycles, we have 1.6 nanometers. So in any case, very thin layers on the surface of the hematite. And if we do nothing, we just have the hematite up to the surface. We characterized very well these films, and we can see that the photocurrents were different. So in all the cases, we have better photocurrents when we have more and more electrocatalysts. However, these photocurrents, they look, and the dark currents, they look kind of tricky. So what we could see is that when we have too much electrocatalyst, which is still not that much, it's just 1.6 nanometers, the photocurrents go down with time, and eventually you have the same photocurrent than the photoanodes without any electrocatalyst. However, if you add very small amount, which is just like a surface modification, because it's just less than 0.7 nanometers, you have better photocurrents and stable photocurrents, as you can see here. And the stability is comparable to that of the pure hematite photoanode. So that was very interesting. We researched that and eventually concluded that what happens if you put too much, which is just 1.6 nanometers. Eventually, when you do the photocurrent measurements, what you are oxidizing is not water or hydroxides, it's actually cobalt hydroxides to cobalt oxyhydroxides. So in order to avoid this reaction, you need to limit the amount of cobalt and iron that you put on top. And so you just do a surface modification, not like a coating. And we did also a lot of kinetics studies. We followed 2 approaches, one using impedance spectroscopy and another using intensity modulated photocurrent spectroscopy. In both cases, we could measure the recombination rates and the charge transfer rates. And we could see in both cases that the recombination rates are lowering when we have the electrocatalyst, especially when you put a lot. But the charge transfer only improves if you control very well the amount of electrocatalyst. So this shows that if you, and in agreement with the photocurrent and dark current measurements, is that if you put too much, yeah, you are lowering the recombination, but this is because the electrons are just, the holes are just used to oxidize the electrocatalyst, and not really to be transferred to the electrolyte. What we want is a transfer, because we want to have more oxygen evolution. And this increased charge transfer is achieved when you limit the amount of the electrocatalyst. So we don't have to care so much about the recombination rates, which are often very discussed in literature. It's more important the charge transfer rate, at least in this case, in which we see that we can have some problems of dark currents. We also saw that we can add an extra layer, an interlayer of gallium oxide, to further boost the photocurrents, which are also related to an increase of the charge transfer kinetics, as you can see with our study. And we also saw when we measured the capacitance of surface states that we have a shift to lower potentials, which is in agreement with having the gallium oxide and the cobalt iron oxide hydroxide controlled amount on the surface, increasing the capacity, the ability of our photoanodes to store charges at its surface, which can eventually be transferred to the electrolyte. So that was for our work for cobalt iron oxide hydroxide. We have also been studying the simultaneous formation of an electrocatalyst, in this case, iron oxide hydroxide. This came a bit by serendipity. So we were working on iron oxide hydroxides as a precursors, as particle precursors for the formation of iron oxide films. And so we were working with these nanorods and then getting these films. And then our postdoc, Dominic Walsh, he tried to modify these nanorods. He added a bit of lactic acid. And as you can see, the nanorods became a bit more amorphous, more ill-defined, and we had by Raman and XRD, we could confirm that they were changing from alpha to beta phase iron oxide hydroxide. And when we used these different nanorods that have been prepared with different amount of lactic acid in the preparation of hematite, so after the calcination, we could see that the films were a bit different. We could see like it was kind of difficult to focus because there was like an extra layer on the surface of the hematite. So we did a lot of TM, and we could see that when you change the formology of the particles that work as precursors, eventually the layers, the hematite has like an amorphous layer whose thickness increases with the amount of lactic acid. So the more lactic acid you add, the thicker is this amorphous layer. That was quite interesting because actually we also saw an increase, an improvement of the photocurrents. We had better photocurrents for optimal amounts of lactic acid. We found the best, it was 0.2 grams in the reaction synthesis. And this coincided with the highest photoelectrochemically active surface areas. So achieving these 10 nanometers of amorphous layer, the final films have higher photoelectrochemically active surface area. And this explains the best photocurrents we achieved. And this was remarkable because we achieved 1.5 million pairs per square centimeter with a kind of a single step, because we just do in one step, we form both the semiconductor and the electrocatalyst. Another semiconductor we have studied are halide perovskites. You know that halide perovskites, they are revolutionizing the field of solar cells because they have very good solar absorption, very good transport of charges, and they are inexpensive to synthesize. And these properties are also interesting for photocatalysis and photoelectrochemistry. So we dedicated some time to study this for electrochemistry and photocatalysis. We started with cesium-lead bromide because it's a good good material that achieves good results in solar cells. It shows very good photovoltage and is relatively more stable than other halide perovskites. But still, it's not. So it's stable because you can heat it up to 400 degrees, but you can still not put it in water. If you prepare films of cesium-lead bromide on top of titanium, FTO, and glass, and you put this in water, it'll take a matter of seconds to dissolve. But we found that we can add carbon layers consisting of mesoporous carbon and graphite, and this way protect the halide perovskite from degradation in aqueous, in liquid water. And this is because the contact angle of these carbon layers, they're hydrophobic, but they still transport the charges. We could measure photocurrents. So you can see at 1.23 electron volts, we achieve more than 2 million pairs per square centimeter. That's like the double of iron oxide. And we can measure these photocurrents for hours. We can also add electrocatalysts on the surface, on the porous surfaces of these layers. and increase the photocurrents and lower the potential onset. Here you can see the oxygen evolution in the photoanodes that we prepared with the halide perovskite protected, and the incident photocurrent efficiency. They were close to 100. I guess we didn't reach 100 because of a lot of problem of product desorption, because they were producing a lot of oxygen, and we could see a lot of bubbles anchored on the surface. And we could see that eventually they were degrading, not because of our carbon layer, but because some water was diffusing through the edges. So this could be improved by changing the configuration, or by improving the mechanical properties also of the carbon layers. So this was very good. Now we are trying to extend this to other different perovskites. We could also see that we know that the halide perovskites, they have very good conduction band for CO2 reduction. So we wanted to use them in CO2 photocatalytic reactors. But we wanted to find a way to prepare the perovskites that is greener without using so much organic solvents. So we developed the use of ball milling for halide perovskites. We use milling balls and milling jars where we put different cesium and lead precursors. We shake these at 500 revolutions per minute for different times. And this way we were able to form cesium lead bromide that was there on the surface of the balls. We could scratch it or disperse it with isopropanol. And this way we could achieve powders of nanocrystals of cesium lead bromide. We could see the different morphologies. So these morphologies were the result of using different precursors or different times or different balls. And we did a systematic study showing the different conditions, how they lead to different morphologies. We also saw anyway that those perovskites, they have a water contact angle of only 0 degrees. They are very hydrophilic. So to increase the hydrophobic character, we asked reduced graphene oxide functionalized with small copper nanoparticles. So we just put copper RGO inside the balls with a bit of isopropanol, and this way we could form composites because the halide perovskites, they were growing on the surface of the reduced graphene oxide. And the final composites, they have an increased hydrophobic character because instead of having 0 degrees, we have a contact angle around 43 degrees. So when we tested these powders for photocatalysis, we could see we could see some CO and CH4 and hydrogen, but it was degrading with time. However, when we had the graphene oxide, the reduced graphene oxide of copper, we had more photocatalysis and also better stability because you can see it's not decreasing with the number of runs, and better selectivity to CH4 because of copper that is known to be a good electrocatalyst that favors the formation of intermediates that lead to CH4. So that was very good. The problem is that cesium lead bromide contains lead cations. So we studied the formation of a lead-free halide perovskite, in this case, cesium silver bismuth bromide. And this way, we could also achieve, following the same approach with copper RGO and ball milling, we could form composites of perovskites, copper, and RGO. And they also obtain good photocatalysis and good stability. Finally, we have also done a lot of work on oxide perovskites, and we have found that we can prepare oxide lanthanum ferrite and oxide praseodymium ferrite photocathodes that show very good photocurrents of 200 microamperes per square centimeter and very high onset potentials at 1.4. So lanthanum ferrite had been studied before, but with lower photocurrents and difficult synthesis. But using Triton X100 and precursors and spin coating, we could obtain very good films. And we also demonstrated that praseodymium ferrite can also be prepared, and it's itself a photocathode for oxygen reduction or hydrogen evolution. And I was not familiar at that time with praseodymium, but apparently it's a material that is abundant. It's in the green area of abundant materials. And it's actually very used in mobile phones. So that's all. So we conclude that we can prepare titania with exposed 010 facets using titania 16 clusters and ACVD We can also use ACVD to prepare iron titanate-based systems where zinc doping has a positive impact to increase the phase of iron titanate and have better photocurrents due to a shallower Fermi level. We also demonstrated we can use cobalt iron oxyhydroxide and gallium oxide to boost transfer kinetics at the surface of hematite anodes. We also demonstrated we can use iron oxyhydroxide modified with lactic acid to form hematite photoanodes with higher photoelectrochemically active surface area and photocurrents because of the formation of an amorphous layer. We show that we can protect halide perovskites with carbon layers to do water oxidation, and also with reduced graphene oxide and copper to prepare powders that do CO2 photocatalytic reduction. And finally, oxide perovskites can be used as photocathodes with high onset potential to reduce oxygen or evolve hydrogen evolution. So that's all. I would like to thank the authors or co-authors or collaborators that were involved in all this work. Here you have all the list. IPSRC and Marie Curie for funding, and my current group, and all of you for your attention. Thank you very much.
Thank you so much for that insightful speech, Doctor. The stage is open for questions. We assume there are no questions for you as of now. If the speakers have any questions later, we will write to you. Is that okay for you, Doctor?
Yeah, thank you very much. Yeah.
Yeah, thank you once